This is the first of two lessons on the Flight Management System, which is often abbreviated to FMS. This one is mainly on components and hardware, whilst the second concentrates on equipment operation. All modern airliners contain a flight management system. It combines various subsystems into one integrated system, designed to provide continuous automatic navigation, guidance and performance management. FMSs can vary considerably from manufacturer to manufacturer and type to type. The system architectures can be different, and different manufacturers often use different names for the same basic components. This makes it difficult to generalize about them, and the details of any particular system will be studied during your type conversion. However, they all contain the following basic subsystems. A flight management computer, or FMC. This is the central processor which combines all the other components into an integrated system. It also carries out the navigation, guidance and performance calculations. A control and display unit, or CDU, for each pilot. This allows them to input information through a keypad and receive information through a display screen. Our arrows therefore go both ways. 2 or possibly 3 inertial reference systems to provide position, altitude, acceleration and velocity information to the flight management computer. An air data computer, or ADC, to give altitude and airspeed information. There are radio navigation inputs, navigation and performance databases in order to provide route, navigation aids and basic aircraft data, and engine and fuel data. The pilots manage this system in order to generate commands to the flight guidance system. This is a generic term which can either mean the flight director display on the electronic flight instrument system, or can mean the autopilot. This is the layout of an early model of the FMS fitted to the Boeing 737-400. And, although it did not have GPS, it was very similar to our basic model. You can see that there is one flight management computer serving both pilots and 2 inertial reference systems. However, here is a later model. The architecture looks more complicated because there are 2 flight management computers, 1 for each pilot, and 3 inertial reference systems. However, the basic components are the same, and the way the system works is the same. The commands generated to the flight guidance system give 2 types of guidance. The first is lateral navigation, or LNAV. This is in the horizontal plane, steering the aircraft left or right as required to follow a route through a series of waypoints to the destination. The second is vertical navigation, or VNAV. This is the vertical profile and takes account of the optimum flight level for the weight and distance, the fuel used, and the diversion requirements. FMS lateral navigation is more comprehensive than the simple waypoint-to-waypoint navigation provided by a first-generation inertial navigation system. The greater computer power available in more modern systems allows a lateral flight plan to include the following: the takeoff runway, including an update of present position on takeoff, the standard instrument departure, or SID, the transition from the end of the SID to the en route flight level, waypoint steering en route, the transition from the top of descent to commencing the standard instrument arrival, the standard instrument arrival, or STAR, the selected instrument approach to the landing runway, a missed approach and go-around, if required, and a flight plan to an alternate airport. Vertical navigation is also complex, and there is a lot of interaction with lateral navigation. We will show some of these facilities by the use of examples. For instance, here is a section of a takeoff and climb profile. If there is a noise abatement procedure at an airport, an aircraft will be required to climb quickly to minimize noise at low level. To achieve this, the climb is carried out at takeoff safety speed plus 10 knots until past a specified waypoint. We will then assume that there is an air traffic control requirement to maintain 250 knots indicated airspeed until reaching 10,000 feet. We need to cross a radio facility called Alpha Bravo Charlie above 4,000 feet. The computer will have to compute whether, with our present thrust, our airspeed of 250 knots will give us the required rate of climb. Next, we must cross Bravo Charlie Delta at 6,000 feet. Above 10,000 feet, we continue with the climb at the aircraft's economical climb speed, which will vary with the weight and static air temperature, and which will be calculated by the computer and passed to the auto throttle. A climb power setting which reduces the N1 by 3% is often used in order to save engine wear. We will assume that, at this weight, this setting gives a climb speed of 302 knots IAS, converting to 0.597 Mach. This is the point at which the Mach number becomes more limiting than the IAS. At the top of the climb, the aircraft is commanded to level flight and is accelerated to the economical cruise speed. Again, this is calculated by the computer, taking into account weight, altitude, and temperature. As the aircraft proceeds along the level portion of the route, as fuel is burnt and the weight reduces and as the temperature changes, the optimum economical cruise speed is continuously updated. There may come a point along the route where the aircraft is now light enough to make it worthwhile continuing the cruise at a higher flight level, subject to air traffic constraints. This is called a step climb. The considerations for the descent are similar. A top of descent point is computed automatically. Speed, distance, and altitude constraints require continuous calculation of required thrust right down to the final approach. A high-speed descent or a fuel economy descent may be selected. We'll now look at some of the components. The first of these is the Control and Display Unit, or CDU. This is the piece of equipment that allows the pilots to communicate with the FMC. It consists of a plasma display and a keypad. Let's start with the display. You can see that, about 3/4 of the way down, there is a horizontal dotted line. Above the line, we have the fields. These are specifically for data entry and are used in connection with the line select keys. Below the line, we have the scratch pad. As the name suggests, it is where we make draft entries and check them before we commit them into the computer. Suppose that we want to enter a gross weight of 61,700 kilograms at startup. We type in 61.7. We can now check it, and if there is a mistake, clear it and re-enter it. When we are satisfied that it is correct, we touch the line select key. The number jumps from the scratch pad to the field. However, the scratch pad also has a second use. The computer is programmed to pass relevant information to the pilot should it be necessary. These are called alert or advisory messages. Alert messages have the highest priority and they identify a condition which must be acknowledged and corrected by the crew before further FMC guided flight is advisable or even possible in some cases. Advisory messages have lower priority and inform the crew of the CDU entry errors or system status. Below the display is the keypad. There are number keys, letter keys, and function and mode keys to select particular pages or functions. There are also 4 indicator lights called annunciators. The first is the display light. The CDU is menu-driven and there are many different pages available. If the page that the crew have selected is not related to the active flight plan leg or the current operational performance mode, The display light reminds the crew that they are not using the optimum page. The fail light illuminates if any FMC failure is detected. The generation of any alert or advisory message causes the message light to illuminate. This will then draw the crew's attention to the scratch pad. Finally, there is a function in the FMS called offset. The aircraft can be programmed to fly parallel to, but a fixed distance from, the FMS programmed track. This could be used to avoid the turbulent wake of the aircraft ahead, for instance, or to increase separation from opposite direction traffic. Unfortunately, the display on the electronic flight instrument system does not make it obvious that the offset is being flown, so the offset light stays on to act as a reminder. The CDUs are used during pre-flight to manually initialize the IRS and FMC with dispatch information, flight plan routing, zero fuel weight, and planned cruise altitude. In flight, they are used to control the FMC and display flight information, and to show alert and advisory messages.